As one of the leading manufacturers of industrial temperature measuring technology, JUMO would like to provide important basic information regarding resistance thermometers and thermocouples in this video. The video shows the functionality of the devices and provides information about the connection and the startup of temperature measuring systems. Resistance thermometers change the ohmic resistance when the temperature changes. The mostly used resistance material for the industrial measurement technology is platinum. The following chart shows the resistance values of common resistance thermometers. The resistance value of a PT100 at temperature 0 centigrades is 100 ohm. At temperature 75 centigrades, 70 centigrades plus 5 centigrades, the resistance value is 128.987 ohm. Furthermore, resistance thermometers like PT1000, basic resistance 1000 ohm, PT500, basic resistance 500 ohm, and PT50, basic resistance 50 ohm are used. Generally, all kinds of basic resistances are possible. After the connection of a PT100 to a field device as an example, we select resistance thermometer as sensor type for the corresponding input. The field device uses a defined direct current. On the basis of the dropping voltage and the Ohm's law, the resistance is calculated. Different linearization possibilities are stored in the field device. When the setting of the linearization is, for example, PT100, the device calculates the temperature subject to the resistance value. Resistance thermometers can be connected to a field device in 3 different circuit versions. The picture shows the so-called 2-wire circuit. In that case, the field device measures the resistance value of the thermometer plus the lead resistance. A higher temperature than the real temperature on the resistance thermometer is measured. The offset can be realized in the device or with help of the setup program. Even after the correction of the measuring value, the lead resistance will change according to the ambient temperature and will influence the measuring signal. In the event of a 3-wire circuit, the voltage drop on a wire is measured. Due to the high internal resistance of the device, the current on the 3rd wire is practically zero. The device subtracts twice half UL from the measured voltage. So the voltage drop of the resistance thermometer and the real resistance value can be calculated. The 3-wire circuit is the most often used circuit version in the industrial sector. Precondition for a current result is that both wires have the same resistance value. Using a 4-wire circuit, the voltage drop is measured directly on the resistance thermometer. The resistance value can be calculated using the voltage drop on the resistance thermometer and the measuring current. The resistance values of the leads and the contact points can differ. The 4-wire circuit has the lowest measuring inaccuracy. Up to a temperature of typically 600 centigrades, a number of resistance thermometers are available. In the event of higher temperatures, thermocouples can be used. We would like to start the topic thermocouples with a short explanation of the thermoelectrical effect. Due to one-sided heating of a wire, the free electrons in this area are moving faster. They move towards the colder wire end. The electron density in the warm wire end becomes lower. The electron density in the cold wire end rises. This results in a negative electric charge emphasis at the cold wire end and a positive electric charge emphasis at the warm wire end. By connecting the cold and the warm wire end to the device, you can try to measure the resulting voltage. The measured voltage is 0 mV. The reason is the same effect in the measurement connection. Due to the difference in temperature, the same voltage arises. Different materials affect a different potential shift. The thermoelectric voltage depends basically on the conductivity of the material. In the example, nickel chrome and nickel aluminium are used for the limbs. The potential shift of the materials is different. The cold end of the nickel aluminium wire is more overloaded by the electrons than the cold end of the nickel chrome wire. The electrons in the nickel aluminium wire can move 4 times faster than the electrons in the nickel chrome wire. The thermoelectric voltages in the nickel chrome wire and in the nickel aluminium wire remain unknown. We measure the difference between the electric charge emphasis. The measured thermoelectric voltage is a dimension for the temperature differential. Using a thermocouple, you can measure a temperature differential, temperature 1 minus temperature 2. Temperature 1 is the measured temperature and temperature 2 is the so-called reference temperature. To be able to measure temperature 1, you have to know temperature 2 and add up the values. Temperature 2 is the temperature of the terminals of the field device. This temperature is measured by an additional temperature sensor. The example shows a JUMO compact controller. The temperature of the terminals, temperature 2, is added on the calculated temperature differential. This is called internal temperature compensation. You just have to select the sensor type thermocouple and the corresponding linearization for the input. The field device calculates the temperature of the thermocouple using the voltage of the thermocouple, the reference temperature, and the defined linearization. So far we assumed that the thermocouple is directly connected to the device. But often connection cables are necessary. For the internal temperature compensation, the second thermoelectric voltage has to be occur on the terminals of the field device. From this it follows that a compensation cable has to be used for the connection, which has to have the same thermoelectric characteristic as the metals of the thermocouple. The reference junction results in the field device. The internal PD100 measures the temperature of the reference junction and the measurement result is corrected. You have to use the corresponding compensation cables. Please consider the polarity. By using several parts of compensation cables and connecting them, for example with luster terminals, new thermocouples arise due to the different material. The voltages are compensated when the different parts have the same temperature. When the temperature can differ, you have to use connectors free of thermoelectric voltage. The connectors are made of materials with the same thermoelectric characteristics as the thermocouple. You have to select the correct connector for the thermocouple considering the polarity. When thermocouples are manufactured as per DIN EN 6584, the color of the compensation cables and the limbs enable you to identify the kind of thermocouple. So for example, the sheath of the often used thermocouple nickel chrome nickel type K has a green marking of the sheath. The positive terminal is green and the negative terminal is white. Furthermore, this chart shows the color coding as per the different international standards. Generally, thermocouples and field devices can be connected using a copper wire. In that case, the reference junction is on the terminals of the thermocouple. The device measures the voltage of the thermocouple minus the voltages of the terminals and calculates the temperature differential. To identify the process temperature, the temperature differential and the temperature of the terminals have to be added up. The field device measures the temperature of the terminals using a further temperature sensor, for example a PD100 connected to the input 2 of the field device. Select external temperature compensation for the thermocouple input. Furthermore, you have to select the input for the reference junction temperature. Often it is reasonable to connect the thermocouple to a temperature transmitter on-site. The transmitter generates the temperature signal as a standard signal, for example 4 to 20 mA. The JUMO product range includes a number of transmitters for installation in terminal heat or transmitters for mounting on rail. When you need further information regarding temperature measurement, please refer to our technical book Electrical Temperature Measurement. This book is available free of charge as PDF document. Thank you very much for your attention. Should you require any further information regarding this video, please do not hesitate to contact me.